हेलो फ्रेंड्स, कैसे हो आप लोग? आई एम चेतन गर्ग. आई एम master teacher here at Vedantu. I welcome you all again to our RMO Flashback series. Right. In this series, today we will be discussing question 1 and question 2 of year 1991 and a very easy and in fact a surprisingly easy question of IMO. Right. So let us start our session. Let's discuss question number 1 of year 1991. I really encourage you, if you have not solved these questions, kindly pause the video, take a genuine time to attempt the question. After that you can come back to view the solution, right? But important is कि आप question को attempt करो, right? So okay, let's start with question 1. And before starting the questions, let me give you some information. We here at Vedantu, we are running pre-RMO, RMO and INMO batches. Those who have not given pre-RMO exam yet, or unfortunately those who are not able to clear the exam in the last year, they can simply visit our website olympiad.vedantu.com. Here there is each and every information regarding the pre-RMO batches, right? And those who have already cleared pre-RMO, we will simply enroll you to the RMO batches, and those who have already cleared RMO, we will simply enroll you to the INMO batches. All you have to do is just mail me your name, class and proof that you have cleared either of the exam, your contact number and address on this email ID chetan.garg@vedantu.com, right? So those who have cleared pre-RMO, they just need to mail me their proof along with these details on this email ID. We will simply enroll you to RMO batches. And those who have cleared RMO exam last year, again they simply mail me these things on this email ID. We will simply enroll you in our INMO batch, right? So okay, let's start our session today. Okay, today we will discuss first and second question of year 1991, right? So this is basically question first of year 1991. This is a standard result. In fact, this is, I guess, Van Nobel theorem, right? The question says that let P is an interior point of a triangle ABC and AP, BP, CP meet the sides BC, CA, AB in DEF respectively. We need to prove something, right? We need to prove that AP upon PD, that will be equals to AF upon FB plus AE upon EC, right? So let's first draw the figure of this question. Let's say this is our triangle ABC, and let's say this is our P point, right? And this P is any interior point, right? So AP meets BC in D and BP meets AC in E and CP meets AB and at F, right? So now we need to prove this AP upon PD, that will be equals to AF upon FB plus AE upon EC, right? So that is the result that we need to prove. Before coming to this question, just let me tell you some concepts of ratio and proportional that you must be knowing till now. That is, if A by B, that is equals to C by D, so that will also be equals to A plus C upon B plus D, right? We can add up the numerators, that will and add up the denominators. We can also say that will also be equals to A minus C upon B minus D, right? So this is a standard result that almost, I hope, all of you must be knowing, right? And apart from this, one more result, that if ABC is a triangle, right, and let's say D is any point, right? D is any point on the BC, right? Then we can say area of triangle ABD upon area of triangle ADC, that will be nothing but that will be the ratio of this BD and DC. I hope ये सबको clear होगा, है ना? Why this is so? Because area is nothing but half into base into height, and height for both these triangle, that is for ABD and for ADC, that will be same, that is H. So we can say that the ratio of the areas will be simply the ratio of the bases that form the two triangles, right? So these two results we will be using in proving this result. Okay, तो start करते हैं. So let's do first AP upon PD, right? Let's take the left hand side of this inequality. We can say this should be equals to the area of triangle ABP, this ABP, right, upon area of triangle DBP. Why is it so? Because of simply this result. You can see triangle ABD, P is any point, right? So the ratio of the area of the triangle ABP and BPD, that will be simply in the ratio of their bases, that is AP and PD. Similarly, we can say area AP upon PD. अगर हम ADC triangle consider करते हैं तो P AP upon PD, this will be equals to nothing but area of triangle APC upon that of area of triangle which one, CPD, right, or DPC, right. Now if you use this fact that if A by B equals to C by D, then we can also say that this will be equals to this, right. So by simply adding these two results, what we will get, AP upon PD, that is nothing but this plus this, that is also equals to this plus this. So what is area of triangle ABP and APC? ABP, this ABP, right, and this APC, this will become a quadrilateral which is not a convex, right. So we can say this is nothing but the area of quadrilateral ABPC, right. The quadrilateral is nothing but like this, which is not a convex quadrilateral. Anyways, this is a quadrilateral, right. And if we add up the denominator, triangle DBP and triangle this DPC, what will this become? This will become the area of the triangle BPC, right. So we have equate left hand side to be equals to this, right, area of this quadrilateral ABPC upon area of this triangle BPC, right. So this upon this, that we have equated, right. Now let's consider what this right hand side will be equals to, right. Okay, so let's go to our next slide. Okay, let's again rename the points A, B, C. That was point P, that was D, that was E, that was F, right. Okay, now consider AF upon FB, right. Now if you see this triangle APF upon triangle BPF, right, or you can say this is nothing but area of triangle ACF. okay, अगर हम बड़े वाली triangle लेते हैं, this area of triangle ACF upon area of triangle how much, BCF, right. You can see because both these triangles will have the same height and the ratio of the area will be equal to the ratio of their bases, right. And we can also say this should be equals to how much, these two smaller triangles, right, that is triangle APF upon triangle BPF, right. Now as we have already said that if A by B equals to C by D, then that will also be equals to A minus C upon B minus D, right. In fact, you can also prove these results by assuming this quantity to be equals to K and just substituting the value of A and D here, right, A and B here. You'll simply get that thing equals to K, right. And in fact, this is the common way to prove the results of ratio and proportion, right. Okay, let's come back to our question. Okay, so we can say this is nothing but this should also be equals to area of triangle ACF minus area of triangle APF upon area of triangle BCF minus area of triangle BPF, right. So what you can say, this will be nothing but it will be simply this area of triangle APC, because ACF minus APF, this will become area of triangle APC upon this will become area of triangle BPC, right. Okay, so AF upon FB, this is nothing but this triangle upon this triangle, right. So similarly, by the same logic, what you can say that area, what else we need, we need AE upon EC, right. So this AE upon EC, by the similar logic, you can say this AE upon EC, that will be equals to area of triangle this ABP, right, area of triangle ABP upon this area of triangle again which is BPC, right. Now we need to add these two things. if we add these two things, what we will get? We will get, okay, we will get AF upon FB plus we will get AE upon EC, right? And since LCM is denominator is same in the both cases, so we will take simply that LCM, triangle BPC, area of triangle BPC. And what is now this area of triangle APC? APC, this triangle, and that of triangle ABP. ABP is nothing but this triangle. This will again become our area of quadrilateral ABPC. Right, so our right hand side is also equals to what? The area of this convex quadrilateral upon area of this triangle BPC. This is in fact we have proved in the last result that AP upon PD, that was equals to this, right? Area of quadrilateral ABPC upon area of triangle BPC. Also the right hand side is also again equals to, as we have proved, AF upon FB plus AE upon EC, that is nothing but area of quadrilateral ABPC upon that of the triangle area of the triangle BPC, right? So simply we can say left hand side is equals to right hand side, right? So this is nothing but, this is I guess when well, theorem, triangle theorem, right? If I'm not wrong regarding the spelling of the name and also about the pronunciation, right? So this is Van Abel's triangle theorem, right? And that is AP upon PD, that will be nothing but AF upon FB plus AE upon EC, right? So that was the question 1 of RMO 1991. Now let's proceed to question 2 of RMO 1991, right? Sure. So that is the question. This seems to be a question of inequalities, right? If A, B, C and D are any 4 positive real numbers, then prove that A upon B plus B upon C plus C upon D plus D upon A, that is greater than or equal to 4. Alright. So most of the students will be thinking whether we have missed something, or is this is the question. Because if this is the question, this seems to be a standard result, right? This is basically nothing but AM greater than or equal to GM inequality, right? And since ABCD are any 4 positive numbers, so A upon B, B upon C, C upon D and D upon A, these will obviously be positive. And if these are positive, we can simply apply AM greater than or equal to GM. So what will be this? A by B plus B by C, AM of these 4 numbers plus C by D plus D by A upon 4, that will be nothing but product of these number A by B into B by C into C by D into D by A whole raised to power 1 by 4, right? As you can see, these all got cancelled out and we are left with 1. So we can simply say A by B plus B by C plus C by D plus D by A, that is greater than or equal to nothing but 4. So have we missed something, or this is the question? Yes, you are exactly thinking on the right track. This is the question. I guess this is the easiest question that RMO has asked till date, right? To nothing, just AM greater than or equal to GM. But most of you are thinking ki this should not come in RMO exam. This is a simple question, right? So, but again, for your surprise, if you are little lucky, then similar question can come in your International Mathematical Olympiad Exam also, right? So as in the starting of the series, I have told you that we will be discussing a surprisingly easy question of IMO. So let's proceed to that question, right? Again, this question is again very easy. This is the question of IMO 2012, which was held on 10th of July. And this is a second question, problem 2 of day 1, right? This is problem 2 of day 1, right? And that was the 53rd International Mathematical Olympiad, and I guess that was held in Argentina, right? Okay, so what the question says, and again this question is also like this, right? So in fact, this is the question that should come actually in RMO, right? And in RMO also this should be considered as an easy question or maximum as an average question. So what the question says? The question says that A2, A3 and so on AN Okay, you are not missing something here. There is no quantity like A1. Okay, the quantity is just starting from A2, right? So maybe this is creating some confusion, or I don't know. Chal. A2, A3 and so on, An are positive real numbers, okay, which satisfy this condition. A2 into A3 into A4 and so on till An, that is product of all these numbers is 1, okay. We need to prove this. A2 plus 1 square into A3 plus 1 cube and so on, An plus 1 power n, that is greater than n raised to power n, right? Okay, so in this question, I guess according to me, there is one thing missing, that n should be greater than 2, right? As there should also be equality. Okay, we will prove this later, right? Why it should be written that n is greater than 2. Okay, now अगर हम इन टर्म्स को कंसिडर करें, let's take a general term ak plus 1 raised to power k. Okay, so we will take this term, right, and we can say that if we apply again am greater than or equal to gm, but not on this quantity, rather break it into k minus 1 more parts, 1 upon k minus 1 plus 1 upon k minus 1 plus and so on till 1 upon again k minus 1. How many terms will be these? These are nothing but k minus 1 terms, right? So if we apply am greater than or equal to gm on these k quantities, so what we will get? We will get the summation of this whole upon k, right? That should be greater than or equal to how much? Ak upon what? K minus 1 power k minus 1 whole raised to power 1 by k, right? Now if you take power k on both sides, right, what we will get simply ak plus 1 power k upon k power k, which we can cross multiply with, this is nothing but ak upon k minus 1 power k minus 1, right? As you can see in the previous slide, right, if we take power k on both sides, this got cancelled out. We will get ak upon k minus 1 power k minus 1. This will become ak, this is nothing but, this is actually equals to ak plus 1, है ना? So ak plus 1 power k, right, upon k power k, which we have cross multiplied with. So we got ak plus 1 power k, that is greater than or equal to k power k upon k minus 1 power k minus 1. This is power basically, right? Not multiplication, this is power, right? Okay, so if we now write these quantities, right, again equality here hold only when this ak is equals to 1 upon k minus 1, right? Only then the equality will hold, because am equals to gm only when all these numbers are equal. Clearly 1 upon k minus 1, 1 upon k minus 1 and 1 upon k minus 1, all these numbers are same. So this should also be equals to ak to hold the equality, right? So now let's proceed. So by this logic, a2 plus 1 whole square, that will be nothing but 2 raised to power 2 upon k minus 1, that is 1 raised to power 1 into a2, right? Similarly a3 plus 1, that will be nothing but 3 cube upon 2 square into a3, right, and so on and so on. So we can say an plus 1 an plus 1 raised to power n, that should be nothing but greater than or equal to n raised to power n upon n minus 1 raised to power n minus 1 into an. Now if you multiply these all inequalities, right, what you get? We will get left hand side, right, left hand side, that is nothing but greater than or equal to, you can clearly see that these factors got cancelled out, right, and so on. What we are left with this a2 into a3 and so on up to an, which is nothing but 1, right, the product of all these number, and we are left with a denominator of 1 power 1 and this numerator, which is nothing but n power n, right? So we have proved that LHS is greater than or equal to n power n. But now here the only catch is we need to prove n. This is strict inequality, but here we are also occurring with the equality, right? So equality will only occur when all these are equal. Instead of greater than, all these are equal, right? And as we have seen, that will only occur when ak is nothing but 1 upon k minus 1. That means a2 should be equals to 1 upon 1, and a3, that should also be equals to 1 upon 2. A4 should be equals to 1 upon 3, and so on. So an should be equals to how much? 1 upon n minus 1, right? But in that case, this thing will not hold, right? Because the product of all these numbers, that was given to be 1, but in that case that is not possible, right? This is simply nothing but 1 upon n minus 1 factorial. And you can see 1 upon n minus 1 factorial, this can be equals to 1 only when n is nothing but how much? Either 1. Okay, 1 is not the case because we are starting with 2, so n can be 2, right? So again, as I have mentioned earlier, that in this question it should be written that n should be greater than 2, or you can say it should be written that n should be greater than or equal to 3, right? Basically one and the same thing, because if n is equals to 2, then we will have the equality here. As you can also verify, if n is equals to 2, then a2 will be simply equals to 1, and our result will be 1 plus 1, that is a2 plus 1 square, that should be greater than 2 raised to power 2, which again is not correct, because 2 square is simply equals to 2 square. So equality will hold only when n is equals to 2. So according to me, in this question it should be mentioned, maybe it could have mentioned, maybe I have, from where which I have taken this question, the source, that may be incorrect, right? So in actual question it should be n greater than 2, right? So again, as you can see, this is a very simple question of am greater than or equal to gm, and this has come as a second question of problem 2 of IMO 2012, right? So friend, that's it from my side today. We have discussed two questions of 1991, first two questions, and one pretty simple question of IMO 2012, right? I hope you have understood this question. Okay, so before ending, okay. One more thing. We can also, there is one more approach to this question, right? We can also solve this geometrically also, right? Let's see, let's consider one thing. Let's assume let's consider ak. Okay, if you remember the result, if you okay, I'll show you the slide. If you remember this result, we have proved this, right? After that we have extended this to a2, a3 and so on, right? Now if I say that I can prove that okay, I'll write this result, ak plus 1, which we have proved, power ak, power k, that was nothing but greater than or equal to k raised to power k upon k minus 1 raised to power k minus 1 into how much? Into it was ak. Okay. So this we have proved, right? So if I say that we can also prove that x plus 1 power x power let's say anything, power k, that is always greater than or equal to k power k upon k minus 1 power k minus 1 into x. Just we have replaced ak by x, right? We can also prove this result with graphs also, right? If someone has good knowledge of graphs, then you can simply say that this is nothing but, let's say this is minus 1. Okay, so the right hand side graph will be like this, the left hand side graph can be like this or this. That entirely depends on the value of k, whether k is even or odd, right? Independent of the effect, we are only interested in x greater than 0, positive values, right? So we'll start, we are not bothering about the left side from minus 1. We are just focusing on when x is greater than 0. So I can say this graph is always, in fact, if I took the limiting case, this graph is always greater than a tangent which is drawn from origin, right? So I can say this, let's assume this line to be y equals to mx, where m will be the slope of the line. Since we can assume this line to be y equals to mx because this is clearly passing through the horizon, right? Now we need to find the value of m when this thing touches the graph of x plus 1 raised to power k, right? So by simple some differentiation, some simple basic calculus, you will come to know that this m is nothing but k raised to power k upon k minus 1 raised to power k minus 1, right? So we can say this this x plus 1 raised to power k, that is this graph, that is always greater than or equal to, okay, this mx. M is nothing but this, so this into x, okay. So simply multiplying this, we will get the result n raised to power n, okay. So this is another method to prove this question, right? So that's it from my side, guys. Before ending my session, let me tell you again that here at Vedantu we are currently running pre-RMO, RMO and IMO batches. Those unfortunately who have not cleared or appeared for pre-RMO exam, they can simply visit our website olympiad.vedantu.com. Here you will get all the information regarding pre-RMO batches, and those who have already cleared pre-RMO, we will simply enroll you to RMO batches, and those who have cleared RMO, we will simply enroll you to IMO batches. All you need to do is just mail me your name, your class, your proof, your contact number and address on this email ID, right? So we will enroll you to the respective batches, right? So thank you guys, thank you very much. That's it from my side for today. We'll meet you in the next session, and in that session we will be discussing question number 3 and question number 4 of RMO 1991. Thank you, bye bye.